Sequence is one that has a last term, so it ends. You could actually count the number of turns that are in the sequence, whereas infinite never stops. It just keeps going. I could draw an example of a finite versus an infinite sequence. So a very common sequence that you should be familiar with is just the counting numbers. 1, 2, 3, 4, 5. That's a sequence. If I want it to be finite, then I would just like stop writing and I'd be done. If I wanted to say like all the counting numbers, so keep going in the sequence, if I want it to be infinite, then I'll do 1, 2, 3, 4, 5, ... So you'll have to pay attention to like, are the sequences finite or infinite? It would be like, is there a ... That means continue the pattern. So then we're thinking, okay, 6, 7, 8, 9, 10, all the way to infinity. Okay, so we're going to work on our skills of just like identifying the pattern. Okay, please look at these examples. I think there might be another one on here. Describe the pattern, so think about it in words, and with your pods, maybe talk to each other, like how can you say it, and then try to predict what the next term is going to be. Sometimes it's easier to predict the next term than it is to describe the patterns in your own words. So, whichever one you want to do first, go ahead and do. Okay, Jayla, how'd you guys describe the first sequence? Okay, add 4 to each term. So the next term, Brianna, is? All right, Tommy, how'd you guys describe the pattern for 1/3, 1/4, 1/5, 1/6, 1/7?
You're just adding 1 to the denominator.
Okay, add 1 to the denominator. So what is the next term, Bo? 1/8. Something, like you might say, okay, yeah, we're adding 1 to the denominator. When we get into the part where we actually have to write the rule, you might also at least say what's happening in the numerator of the fraction. What could you say about the numerator of this fraction? It's what? It remains the same. The numerator is always 1, right? Like that is a pattern that it stays the same. Okay, so think about that. Sometimes when you see a fraction, you might want to talk about the numerator and the denominator. Okay, all right, and then how did you describe the pattern for our next one? Dylan?
Alternating between adding and subtracting increasingly large even numbers.
Okay, alternating positive and negative is 1. And then what was your next part?
Increasingly large even numbers.
Increasingly
large even numbers. So alternating between adding and subtracting even numbers.
Oh, because you're
2
subtracting
4,
2,
6
adding 4, subtracting 6, adding 8. Okay, so then I'm going to have to change this. Alternating, add and subtract, hang on, even numbers. Okay, so we did what first? Minus 2? Minus 2 plus 4 minus 6 plus 8. And then, did anybody describe that differently?
We described it as it was just the next odd number, so like 1, 3, 5, 7, 9, 11. It would be like 1, negative 1, 3, negative 5, 7,
Okay, so you still had to say something about alternating signs, right?
Yes.
Okay, so you had the alternating signs, the plus or minus. And then you're saying
It was just like the next odd number.
the next odd number. Okay, so this is interesting. Using Dylan's rule, we see we're at the plus 8 right there. So our next step should be minus 10, which his next number would have been a negative 5. Was that going to be your answer, Maddie, with your pattern? Yeah. So are there some sequences where in our own words we can describe things differently? Yes, that's okay. The one thing I want to impress upon you is still you have to look at this sequence and determine the pattern. If you're really struggling, because we're going to do the mathematical part of it next, if you're really struggling with writing I call it the rule for the sequence, then go back to your own words and how would you tell somebody what's going to happen next? And then you try to put that into a mathematical expression. Okay? And that's where you can kind of bridge that gap between how do I do this problem. Okay, so we're actually going to come back to these here in a little bit, but we're going to talk about some math stuff now. And one of those things that we need to discuss is called sequence notation. So sequence notation is different than what we've been using previously. We've been really focused on function notation. Remember, function notation is f of x. Okay, and we can say g of x, h of x to name different things. But the beauty of function notation is that you can say like f of 3, and then everybody knows that's the y value when x is 3. So we have a new notation in sequences. We use A most commonly, but you could name a different sequence. Like if one of your sequences was A, you could call your other one B. You could use B sub n or C sub n, so you can name it any way you want. Okay. But then it has, instead of like the parentheses, like function notation with the x in there, it has a subscripted n. So this little n is going to be below the regular line of text, okay? And it means the nth term, okay? So we can say this is the nth term. So depending on what number you put in for n, that's going to mean that you're talking specifically about a different term. So I have like a sub 1, a sub 2, okay, and then I think the last one is an a sub 15. See if I can make that smaller. Move it up. So when you see these things here, this would mean if you see something labeled a sub 1, this is the first term, the second term, and then this one would jump down to be the 15th term, way far out in the sequence. Occasionally, you might work with a sequence where you have an a sub 0. And a sub 0 would mean the 0 term. That one sometimes is hard for us to comprehend. What does the 0 term mean? It's really the thing that comes before the first term. And likewise, one could argue potentially that you could have an a sub negative 1. But generally in sequences, you're going to start at n equals 1. Because don't you think the sequence has a first term? okay, like we saw on all the other examples. Okay. So those are our notations for like y or f of x. Okay. Now, we're going to be focusing on rules in our upcoming sections 8.2 and 8.3 this week. And so there are two kinds of rules that typically mathematicians are going to work with. One is called explicit. Don't worry, it's not like bad explicit. Good explicit. And the other is called recursive. Generally, you'll be working to get explicit formulas. Okay, so if you want to highlight that, a lot of times when you read directions, it'll say like write the explicit rule, write an explicit formula. Okay, and what explicit means is you can plug in n, right, from your a sub n. So like if you want the 15th term, you can plug in 15 and immediately get a sub n. So it's just kind of like a regular function, okay, notation where it's like, okay, here's the function, plug in your x, get out your y. So it's like, here's the sequence rule, plug in n, whatever term you want, and it'll chug out a sub n. There are some sequences where an explicit rule is really hard to do, like that Fibonacci sequence we saw, where Jacob was telling us add the two previous terms together. It's really hard to write that rule explicitly, okay? So then sometimes we use something that's called a recursive rule. To get the nth term, you must have the term before it. So it's like if I wanted the 15th term, the only way I could get the 15th term is if I knew the 14th term. And in order to get that 14th term, I would need the 13th term, and the 12th term, and the 11th term. So it's like you can't just jump ahead to the 100th term in a recursive rule. You need the term that comes before it. Okay, so you're going to be really focused on writing these rules that are considered explicit. Okay, we're going to go back in just a little bit to those old examples that we did with the sequences where you told me to sequence in words and we predicted the next term, and we're going to try to write a rule for that. But before we do that, I'm going to show you some extra examples. I'm going to come back to that one at the end. I'm going to show you some examples of the sequence notation. Okay, so here are 3 sequences. You can jot them down. Just so you kind of get the feel for sequence notation. All of these sequences are considered explicit. If I gave you a recursive sequence, I'll show you one on the board here at the end. If I gave you a recursive sequence, I could tell it's recursive because I would need to know like a term to start. So usually it starts with like a sub 1 equals 5, and then it tells you how to get to the next term. Okay, so these are sequences where the rules are already provided. These rules are examples of explicit rules. Don't they just kind of look like regular old functions? Well, some of them look like regular old functions. This one maybe doesn't. But we know what to do with that. It's asking us to write the first 5 terms of the sequence. So if I wanted a sub 1 here, the first term, I would plug in 1 for n. And the first term is 1. And if I wanted the second term, plug in 2, and the second term is 4. And if I wanted the third term, plug in 3, and I'll get 7. Are you noticing a pattern? It's going up by 3 each time. So at some point you might recognize what the pattern is as you're like plugging in. And so we know that the 4th term is going to be 10 and the 5th term is going to be 13. Okay, if we wanted to double check it, plug 5 in here. That would be 15 minus 2, which is 13. It works. Okay. Doesn't that make sense that these 5 terms, they're going up by 3 each time? Because what does this function look like, 3n minus 2, that you have studied quite a bit? It looks like what? A linear function. It looks like a line, and a line goes up by a constant slope, right? So that's kind of like my rise over run. It's how much I'm increasing. Can you guys get me the 5 terms for the next 2 sequences? Remember back when we were looking at those sequences in the warm-up and we saw that perfect square one? And you remember Dylan pointed out a sequence he was describing. It's going up by odd numbers. Now it's starting at 3. It went up by 3. It went up by 5. The next one would go up by 7. And the next one would go up by 9. If you're not sure that that actually works, you can always just do the work, right, for the other terms. Okay, but sure enough, it does work, right? We go up by 7, we go up by 9. Okay, so again, that is a super helpful pattern if you notice that, because like if I gave you the sequence 0, 3, 8, 15, 24, a lot of people don't know how to write a rule for that, but they'll notice, like, they'll describe the pattern in their own words. They'll say it's going up by odd numbers. Hint to yourself, if it's going up by odd numbers, it has something to do with perfect squares. So see, the rule has an n squared, but it isn't equal to the squares, it's equal to 1 minus the squares. Or sorry, the squares minus 1. Okay, and then remember this guy, this is our old factorial friend. Okay, so a sub 1 equals 1 factorial over 2, that's 1/2. Is it okay for a term in this sequence to be a fraction? Sure. Okay, this one would be 2 over 2, which we would reduce to be 1, so always simplify it. A sub 3 will be 3 factorial over 2, that's what, 6 over 2, so 3. What's 4 factorial? You guys know this one. Do it a lot. 24. 4 times 3 times 2. So 24 divided by 2 is 12. And then 5 factorial. I know we did that one a lot too. 24 times 5. 120. Okay, so certainly you could get out your calculator and calculate factorials, but I think you probably do that okay. So we've got 1/2, 1, 3, 12, and 60. This one would be a lot harder for people to figure out how to write that rule, the factorial, but there is some kind of connection with the factorial here. Notice that if you take 1/2 times 2, you get 1. If you take 1 times 3, you get 3. 3 times 4 is 12, 12 times 5 is 60. So it's like always got that extra number that's being multiplied. And that's really hard to see that that's actually coming out to be a factorial. But there is some like benefit here to looking at those patterns. Okay, so that's given the rules, generate the terms. I'm going to have you go back to those 3 that we had at the beginning. Can you try to write a rule for these? Okay, so A sub n equals. And sometimes you just got to think outside the box. You got to think about what the pattern is. Okay, you got to try something and then attempt it for like the next term. I think we have like 4 or 5 terms on these, so try it for the 5th or the 6th term and see if it actually works. I'll give you some time to kind of debrief with your pods and come up with some ideas. This is where sequences in series can get a little bit tough. You gotta think for yourself. No one can do it for you. There is some trial and error in the beginning. Try A sub n equals and jot something down. Be right back. You guys got any rules for me? Okay, what did you say for the first one?
A sub n equals 4n minus 2.
Okay, now notice. How did we describe that in our own words? It was going up 4 every time. So you're tempted in your rule, I'm guessing in the beginning a lot of you wrote like a plus 4 somewhere. But the trouble is, if you want to get to like the 100th term, you actually have to add 4 a lot of times, right? So then we did those other examples where we had rules and we came up with first 5 terms, and we actually did one that was going up by 3 each time. and it looked like a linear function. So this one is going up by 4 each time. It should look like a line. Okay? 4n is the number of times that you add 4. If you add 4 over and over again, it becomes multiplication. Repeated addition is multiplication. Just to double check your work, try it out for like a sub 1. 4 times 1 minus 2, that's 4 minus 2 or 2. Works out, right? Try it for a sub 4. 4 times 4 minus 2. That's 16 minus 2, which is 14. We said our next one would be 18. Try it for a sub 5. That would be 4 times 5 minus 2. 20 minus 2 is 18. It actually works. How did you come up with the minus 2 part, Tommy?
Well, because the first term is 2. So 4 times 1 is 4. And then I had to get it to 2, so I subtracted 2.
So if you notice that you're adding the same thing every time, you're going to start with that slope part, 4n, like Tommy did, and then plug in 1 and see what happens. You might have to add something or subtract something to bring it up or down. Did any groups come up with something for the second one? Yeah, what'd you guys say? Dylan?
1 over n plus 2.
Okay, so try it out. A sub 1 equals 1 over, so my n is 1 plus 2, that's 1/3. It works. Let's try it for a sub 5. 1 over 5 plus 2, that's 1 over 7. It works. Try it for another one. We said the next term would be, what, 1/9, right? So that would have been the 6th term. Sorry, 1/8 we said it would have been. That would have been the 6th term. So we would do 6 plus 2 in the denominator and get 8. Okay, seems to work. Yeah, I like it. Okay. Did anybody come up with anything for the last one? That one is pretty tough. Some people might write actually like 2 separate rules. Like you could write a rule for the odd terms and a rule for the for the even terms, because then the odd terms rule would just be like the positive version of the odd numbers, and the even terms would be the negative rules. I'm probably not going to give you something so complex on a quiz or a test. You can also use, like for alternating signs, -1 to different powers, because like -1 to the first is odd, but -1 squared is even. So if you take like -1 to the n or -1 to the n plus 1, you can alternate your signs. Okay, but I'm more concerned about examples 1 and 2. Okay, all right, we got one last thing to chat about. Oop, must be at the bottom of this one. Graphing sequences. Okay, so the one thing I want to point out about graphing sequences is it's just kind of like graphing a function, right? You have an x and a y, but in graphing a sequence, you have an n and an a sub n. Okay. Now notice what I drew for my graph here for my sequence. It's only the positive quadrant, like the first quadrant, because like I said at the beginning, we're going to assume most of the time that we start at the first term. So most likely, you're going to start at a point 1 to the right, and then you can do 2, 3, 4, 5. Okay. So that's like the different terms that or like what terms you are addressing. And then a sub n is like your actual value in your sequence. So what was, we had one up here. These are the ones where we did the first 5 terms. Okay, a sub n equals 3n minus 2. And we had 1, 4, 7, 10, 13 for our first 5 terms. So then we can plot those. This is like a sub 1, a sub 2, a sub 3, a sub 4, a sub 5. We can plot those as ordered pairs. 1, 1, 2, 4, 3, 7. And so I'm going to 1, 3, 4, 5, 6, 7. Put some points there. So there's a point at 1, 1. There's a point at 2, 4. There's a point at 3, 7. And what the next one would be like 4, 10. And then 5, 13. My graph is not very good. What does it sort of look like, or what should it look like? Since it's going up by 3 every time. It should be a straight line. Maybe I got off after I didn't have. Maybe I should just delete those. Should look like a straight line. Okay, but here's the one big difference. Oh, can't spell today. Sequence graphs are discrete. And we really don't spend a lot of time doing a lot of discrete graphs anymore. Maybe we did back in like middle school if we were doing like scatter plots or algebra 1. But it's been a long time since we left a graph unconnected. Okay? If you're asked to graph, you're literally just plotting the points for the different terms. Don't connect them. Why wouldn't I want to connect them? Yeah, if you connect the dots, you're saying there's points in between. So you're saying there's a 1.2 term and a 1.99 term. And we're just saying there's a first term, a second term, a third term. We're going to jump a term every time, right? So always leave it as discrete. Do not connect the dots. Okay. And sometimes they might look like lines, and other times they won't. So like if you were to graph our n squared minus 1 or our n factorial divided by 2, those are not going to look like regular straight lines. Okay. Any questions for me on sequences today? You got a homework assignment, it's on your gold sheet.